All right, welcome to the deep dive. Today, we're really going where few have dared to go before, to the intersection of quantum computing and machine learning. Buckle up, because we're about to explore how the bizarre but amazing world of quantum mechanics might just revolutionize how AI actually learns.
Oh, absolutely. We're diving deep into the mind-bending concept of quantum-enhanced stochastic gradient descent, better known as QSGD.
And to guide us through this dense theoretical jungle, we're using Jörg O. Schneppat's essay, QSGD, Quantum Enhanced Stochastic Gradient Descent. You can find it linked in the show notes.
A fantastic read. Schneppat does a great job breaking down some very complex concepts.
So for our listeners who are already knee-deep in AI and wrestling with mountains of data, you know that machine learning is all about teaching computers to learn from data. And the engine that makes this learning happen, the workhorse of AI training, is Stochastic Gradient Descent, or SGD.
Right, SGD. It's a fundamental algorithm that helps AI models refine their understanding of the world, essentially minimizing the errors they make as they learn.
Okay, let's try to make this tangible. Schneppat lays out the core mathematical equation of SGD. Say plus 1 thetate. Don't worry, we're not going full math class on you, but the basic idea is this. Thetate represents the current settings of our AI model, kind of like the knobs and dials.
Exactly. And A, the learning rate, is how much we adjust those knobs with each step. Too big a change, and you might overshoot the best setting. Too small, and learning takes forever.
And that last part, the theta, that's the gradient, it's essentially a compass telling us which direction to turn those knobs to reduce the errors to make the model better.
So the algorithm takes a step in the opposite direction of that gradient, a step towards better performance. And what makes SGD so powerful, especially when dealing with massive data sets, is the stochastic part. Schneppat really emphasizes this.
Right, the stochastic bit. Instead of looking at all the data at once to figure out which way to go, SGD randomly picks a small chunk of data, maybe just a few data points, to estimate the gradient.
Like navigating a complex landscape by taking quick glimpses around you, rather than mapping out the entire territory before taking a single step. Much more efficient.
Exactly. And this efficiency, as Schneppat points out, is what makes SGD so well suited for those huge data sets we see in modern AI, like training large neural networks.
And it's not just about efficiency. It's also about flexibility. SGD can handle those really complex learning problems where the path to the best solution isn't just a straight downhill slope. It can navigate those twists and turns.
Plus, as Schneppat highlights, SGD can adapt on the fly as new data comes in. It's like learning as you go, constantly refining your understanding. But there's a catch. There are some inherent limitations to this approach that Schneppat doesn't shy away from discussing.
That's right. Because we're only looking at a small piece of the data at each step, our gradient, our direction, is inherently noisy. It's not a perfect compass.
So instead of a smooth descent, it might be a bit more like a drunken stumble toward better performance, not always the most direct route.
Exactly. And this noise, as Schneppat explains, can slow down the learning process. Plus, there's the risk of getting stuck in what are called local minima.
Local minima, those are like little dips in the learning landscape, right? Not the absolute best solution, but good enough to fool the algorithm into stopping there.
That's it. And even though the randomness of SGD can sometimes help it jump out of those traps, it's still a major challenge.
Yep.
And let's not forget the hyperparameters.
Hyperparameters, those settings that control how the algorithm learns. As Schneppat emphasizes, getting those just right can be a real headache.
It's a bit like fine-tuning a radio signal, trying to find the sweet spot. And with larger data sets and more complex models, the tuning gets even harder, the risks of getting stuck increase, and the learning time can become impractically long. This is where Schneppat brings in the potential of quantum computing to overcome these limitations.
Okay, so let's dive into the quantum realm. We know quantum computers are fundamentally different beasts. How does this difference actually help?
Well, Schneppat does a really good job explaining the fundamental weirdness of quantum mechanics that makes this possible. Think of superposition, where a quantum bit, or qubit, can be in multiple states at once.
It's like a coin spinning in the air. It's both heads and tails at the same time until it lands.
A good analogy.
Yeah.
And this ability to be in multiple states simultaneously, combined with entanglement, where qubits are linked in a way that defies classical physics, allows quantum computers to explore many possibilities at once.
So instead of taking one step at a time based on a noisy estimate, we can, in theory, explore multiple directions simultaneously. Is that what QSGD is all about?
Exactly. And that's the potential aha moment that Schneppat hints at. QSGD aims to use this quantum weirdness to calculate those crucial gradients much faster, use fewer resources, and potentially avoid getting stuck in those local minima.
So we're taking that SGD equation, t plus 1 theta tat, and giving it a quantum upgrade.
Exactly. SNEPHAT lays out the mission quite clearly. We're going to unpack how this quantum-enhanced SGD works, the theory behind it, how those quantum principles actually fit into the process, and what the potential benefits are. But we'll also look at the practical challenges, where it might be most useful, and the hurdles we still need to clear.
Sounds like a plan. So let's start with solidifying our understanding of regular SGD. We've touched on it, but let's dig a little deeper. SNEPHAT spends a good chunk of the essay explaining the core mechanics.
Right. And a good way to appreciate SGD, as SNEPHAT does, is to compare it to classical gradient descent. In classical gradient descent, you calculate the gradient, that direction, by looking at all the data points every single step.
Which sounds thorough, but incredibly inefficient with the massive data sets we're dealing with these days. It's like trying to climb a mountain by meticulously surveying every inch of the terrain before taking a single step.
A great analogy. SGD, on the other hand, is like taking quick snapshots of the surrounding terrain and adjusting your path accordingly. You might not always take the most direct route, but you're definitely much faster.
And this speed and flexibility, as SNEPHAT emphasizes, are crucial for handling those huge data sets and those complex, curvy learning landscapes we encounter in modern machine learning.
Absolutely. But we can't forget the trade-offs. That noise in the gradient, because we're only looking at a small sample of the data each step, the risk of getting stuck in local minima, and the sensitivity to those hyperparameters, those are all challenges that QSGD aims to address.
Okay, so now we arrive at the heart of the matter. Quantum-enhanced stochastic gradient descent. How does this even work? How do we inject quantum mechanics into SGD?
Well, as SNEPHAT defines it, QSGD uses quantum algorithms to speed up the calculation of those gradients and potentially optimize other parts of the learning process. The fundamental idea is to leverage quantum computers' ability to perform many calculations simultaneously, thanks to superposition, to get those gradients much faster and with fewer resources.
Okay, so we're using quantum computers to basically cheat the system and calculate lots of possibilities at once. And one of the key concepts SNEPHAT introduces is this idea of quantized gradients. What exactly does that mean?
Right, quantized gradients. It sounds fancy, but it boils down to this. Instead of representing the gradient information as regular bits, we use the quantum properties of qubits, particularly superposition and entanglement, to encode that information in a much more compact and efficient way.
It's like squeezing much more information into each qubit compared to a classical bit. So how does this help with actually calculating those gradients?
Well, think about it this way. By putting qubits in superposition, a quantum computer can effectively perform multiple parts of the gradient calculation simultaneously. SNEPHAT mentions some specific quantum algorithms that are often used, like quantum phase estimation, QPE, or the Harrow-Hasidim-Lloyd, HHL algorithm.
So instead of trying one direction at a time, we're exploring multiple potential paths simultaneously. It's like having a team of scouts fanning out to find the best route down the mountain, rather than just one guy stumbling around in the dark.
A great way to visualize it. And SNEPHAT even presents a general equation for this quantum-enhanced gradient descent. T plus 1, mathcalq, appletat.
Okay, so it still has that familiar structure of updating our model based on the gradient, but now that gradient, that mathcalq, is calculated using the magic of quantum computation. But how do we even get those classical numbers, our model settings, and the data itself into those qubit states?
That's a crucial step, and SNEPHAT goes into some detail about it. Remember, a qubit, the basic unit of quantum information, can exist in this superposition state. Psi wrangle, alpha wrangle, plus beta 1 wrangle. So we need to translate those numbers that represent our model and the data into this kind of quantum language.
It's like taking a regular sentence and encoding it into Morse code so that it can be transmitted using those short and long beeps.
A perfect analogy. And once we've done that, we can apply various quantum operations like Hadamard gates and controlled rotations to manipulate those qubits in parallel. This allows us to explore that vast space of possible solutions much more efficiently than we could classically.
And SNEPHAT even mentions using Grover's algorithm, which I've heard of before, to speed up this process. How does that fit into the picture?
Grover's algorithm is a famous quantum search algorithm. Think of it as finding a needle in a haystack, but in the quantum realm. SNEPHAT suggests that it can be used to speed up the search for the optimal hyperparameters, those settings that can make or break the performance of our AI models.
So instead of trying different values one by one, a quantum search could potentially find the best combination much faster. That sounds like a huge time saver.
It could be. And that brings us to the overall theoretical speed advantage of QSGD. Schnepped does a really nice job of comparing the computational demands of classical SGD and QSGD.
This is where we start to see the real potential for revolutionizing AI, right?
Absolutely. Schnepped talks about time complexity, basically how the time it takes to train a model scales with the size of the data and the number of parameters in the model. For classical SGD, it's typically linear. If you double the data, you double the time.
Okay, makes sense. But QSGD, if we can pull it off, promises a much more favorable scaling.
Exactly. In idealized scenarios, Schnepped points out that QSGD could potentially achieve a time complexity that scales like the square root of the dataset size.
So instead of doubling the time when you double the data, it might only increase by a much smaller factor. That's a huge difference when we're talking about those massive data sets we see in big data and modern AI.
A game changer, potentially.
Yeah.
And not only that, the dependence on the number of parameters in the model, which can be in the billions for those massive neural networks, also becomes much more manageable in QSGD.
Okay, so faster training, potentially lower resource usage. It's starting to sound too good to be true. Schnepped does bring us back down to earth a bit by discussing some of the challenges and potential error sources. It's important to be realistic, right?
Absolutely. Schnepped is very upfront about the fact that current quantum hardware is not perfect. It's prone to noise and errors, which can directly affect the accuracy of those quantum calculated gradients. Techniques like quantum error correction, and Schnepped mentions the surface code model specifically, are being developed to address this, but there's still a long way to go.
And I've heard that those delicate quantum states are also very susceptible to environmental interference. What's that called again? Decoherence?
That's right. Decoherence is a major challenge. It's like those qubits losing their quantum mojo, the information they hold, due to interactions with the environment. Researchers are exploring ways to perform those quantum computations much faster and better isolate those qubits to combat decoherence.
And it's not just the hardware, is it? Schnepped also points out that the quantum algorithms themselves might introduce some level of approximation, which could lead to less than ideal solutions.
Yes, that's an important consideration. Many of the quantum algorithms we might use for QSGD rely on approximations to make them practical on near-term quantum computers. This means carefully tuning the parameters of these algorithms is crucial to getting the best possible results.
And finally, there's the initial hurdle of getting all that classical data, our training sets, into those quantum states. Schnepped refers to this as the cost of qubit encoding.
It's a non-trivial step. Translating all that classical data into the language of qubits can be a computationally demanding task in itself. We need both better quantum hardware with more qubits and more efficient algorithms for this encoding process to make QSGD truly practical.
Okay, so while the theory of QSGD is exciting, the practical implementation still faces some serious challenges. And Schnepped goes into detail about what kind of quantum hardware we actually need to make this a reality.
Absolutely. Schnepped outlines several key requirements. First, we need quantum computers with many more qubits, thousands or even millions, to handle those complex AI models. And those qubits need to be stable, maintaining their quantum states for longer periods. That's what's called coherence time.
It's like having a larger canvas and paints that don't dry out too quickly so we can create our quantum masterpiece.
A perfect analogy.
Yeah.
And those quantum operations, the gates and measurements, need to be much more precise with far lower error rates. Error correction techniques are crucial here. Then, we need high connectivity between those qubits so they can be entangled effectively for those parallel computations. And finally, we need seamless integration between quantum and classical processors, a hybrid architecture where each part does what it's best at.
Okay, so a tall order for quantum engineers. Schnepped does mention some promising platforms that are paving the way.
Yes, some really fascinating developments are happening. Schnepped highlights IBM Quantum with their superconducting quantum computers, like the IBM Osprey with its hundreds of qubits. They're pushing the boundaries of scalability and error correction, which is key for QSGD. Then there's Google's Sycamore processor, known for its low error rates and its demonstration of quantum supremacy.
Quantum supremacy, that's where a quantum computer does something that's practically impossible for a classical computer, right?
Exactly. And that kind of precision is really valuable for experimenting with QSGD and other quantum algorithms. Then there's IonQ, using a different approach with trapped ions, achieving very high coherence times and operational fidelity.
So lots of different approaches, all pushing the boundaries of what's possible. But as Schneppet points out, the ability to scale up the number of high-quality qubits is still the biggest bottleneck.
That's the crux of it. We need more qubits, better stability, and lower error rates to unlock the full potential of QSGD for those real-world AI challenges.
Now, let's dive into the algorithmic design of QSGD itself. Schneppet gives a high-level outline of the steps involved. How does it actually work in practice?
Well, the overall structure is similar to classical SGD. We initialize our AI model's parameters, encode the training data into those qubit states, and then for each training step, we select a batch of data. But the crucial difference, as Schneppet emphasizes, is in the next step, calculating the gradient.
This is where the quantum magic happens, right?
Precisely. Instead of those classical methods, we use a quantum algorithm, potentially like the HHL algorithm Schneppet mentioned, to compute the gradient. This leverages the parallel processing power of the quantum computer. We then use that quantum computed gradient to update our model's parameters, just like in classical SGD. And of course, managing errors and decoherence throughout the process is crucial.
Okay, so the basic loop of updating the model based on gradient information remains, but the gradient calculation gets a quantum boost. What are some of the other key differences that Schneppet points out between classical SGD and QSGD?
Schneppet highlights several important distinctions. We've already discussed the most significant one, the gradient calculation itself. But the way data and parameters are represented is also fundamentally different. In QSGD, they're encoded as qubits, which can have significant implications for computational efficiency, especially for high-dimensional problems. And of course, the underlying hardware is completely different, requiring this intricate dance between classical and quantum processors in a hybrid architecture.
And Schneppet also goes into the computational demands, comparing classical SGD and QSGD in terms of both time and memory usage.
Yes, and to recap, Schneppet reiterates the potential for a significant reduction in time complexity with QSGD, especially for large data sets and complex models. This translates into faster training times, which is a major advantage. And while QSGD could lead to lower memory requirements because of the way information is stored in qubits, that still depends on the progress of quantum hardware development.
Okay, so faster, potentially more efficient. How would this impact the training of those massive neural networks that are becoming increasingly common?
According to Schneppet, the impact could be huge. Faster gradient calculations mean faster convergence, potentially slashing training times for those giant models. The ability to efficiently optimize hyperparameters using quantum algorithms like Grover's could also save a lot of time and resources. And perhaps most excitingly, QSGD might allow us to train models that are currently impossible to handle with classical computers due to their sheer size and complexity.
Wow, so we could be talking about a whole new era of AI pushing the boundaries of what's possible. And Schneppet doesn't just talk about the general impact, he also explores specific areas where QSGD could be particularly beneficial.
Absolutely. Schneppet outlines several key domains where QSGD's unique advantages could lead to significant breakthroughs.
Let's start with those massive deep learning models like GPT and vision transformers that are really pushing the limits of current computing. What are the specific challenges they face that QSGD could address?
Well, as Schneppet explains, training these behemoths with billions of parameters requires immense computational resources and takes a long time. QSGD could significantly reduce those training times, enabling faster development and experimentation. Its ability to optimize those crucial hyperparameters more efficiently could also lead to better performing models. And ultimately, as Schneppet suggests, QSGD might be the key to unlocking the full potential of these models, leading to significant advances in natural language processing, image recognition, and content generation.
It sounds like QSGD could be the missing piece of the puzzle for those really cutting-edge AI applications. Schneppet also talks about potential applications in finance, a field that's no stranger to complex computations and large data sets.
Right. Schneppet highlights several problems in finance where QSGD's efficiency could be a game changer. In portfolio management, for example, it could allow for much faster optimization of investment strategies, especially when dealing with large and diverse portfolios. In risk modeling, it could lead to quicker and more accurate assessments of market and credit risks, which is essential for making informed decisions in a rapidly changing financial landscape. Schnepp majorly mentions potential applications in pricing complex derivatives and optimizing trading strategies.
So not just making things faster, but potentially making better decisions, which in finance can translate into significant gains. Schneppet then takes us to a less obvious application area, material science, and quantum chemistry.
And this connection is fascinating because, as Schneepat points out, optimization is at the heart of many problems in these fields. For example, finding the lowest energy configuration of a molecule is essentially an optimization problem. QSGD could significantly accelerate this process, potentially leading to faster discoveries of new materials and more efficient simulations of chemical reactions.
So we're talking about not just improving algorithms, but also accelerating our understanding of the physical world itself. That's pretty profound. And finally, Schneepat discusses the potential of QSGD for big data analytics and even edge computing. It's quite a range of applications.
It is, and it highlights the versatility of this approach. For big data, where we're dealing with massive datasets, QSGD's ability to process information faster, thanks to its more favorable scaling behavior, could be crucial for real-time analysis and decision-making. And for edge computing, where devices have limited resources, QSGD could enable more sophisticated AI to run locally without relying on powerful servers. This could have huge implications for things like autonomous vehicles and smart home devices.
Okay, so a wide range of potential applications, from massive cloud-based systems to tiny devices at the edge of the network. But as we've discussed, there are still some significant hurdles to overcome. Schneepat dedicates a good portion of the essay to these critical considerations.
Right, and it's important to acknowledge those challenges. Schneepat starts by outlining the limitations of current quantum hardware. The relatively small number of qubits, their susceptibility to errors, their short coherence times, and the slow speed of operations all pose challenges for implementing QSGD for complex, real-world problems today.
And it's not just the hardware itself. There's also the issue of integrating QSGD into the existing infrastructure and tools we use for machine learning, right?
Exactly. Schneepat discusses the need to develop those hybrid architectures where classical and quantum computers can work together smoothly. We also need to figure out how to efficiently translate between the way data is represented in classical computers and the way it's encoded as qubits. And the lack of standardized software libraries for quantum-based optimization makes development more complex.
Schneepat also raises concerns about security and privacy, which are crucial aspects to consider as quantum computing becomes more prevalent in machine learning.
Absolutely. Schneepat talks about potential vulnerabilities that quantum algorithms might introduce to encryption methods. There are also risks associated with data encoding, and as quantum computing matures, we need to develop new guidelines and regulations, especially in industries where data sensitivity is a major concern.
And looking beyond the immediate technical and integration challenges, Schneepat outlines some of the key open research questions that still need to be addressed for QSGD to reach its full potential.
Right, there's a lot of exciting work ahead. Schneepat highlights the need to improve QSGD's scalability to handle even larger and more complex problems. We need to develop more efficient quantum algorithms specifically designed for QSGD and better error correction techniques. And we need to explore how broadly applicable QSGD might be to other types of optimization problems beyond machine learning.
So a lot of potential, but a long road ahead. And that brings us to Schneepat's perspective on the future of QSGD. Despite the challenges, there's a sense of optimism, a belief that this technology is worth pursuing.
Absolutely. Schneepat anticipates the continued development of QSGD with a near-term focus on those hybrid quantum classical algorithms, combining the best of both worlds. We might see specialized versions of QSGD tailored to specific problems and new ways to integrate QSGD with other quantum algorithms to tackle increasingly complex tasks.
And of course, the future of QSGD is tied to the advancements in quantum hardware itself, which is rapidly evolving.
That's key. Schneepat emphasizes the need for more qubits, better stability, lower error rates, and faster operation speeds. And the development of more energy-efficient quantum hardware will also become increasingly important as these systems become more powerful.
So a lot of exciting developments on the horizon. What long-term impacts on machine learning and optimization does Schneepat envision?
Schneepat suggests that QSGD could become the go-to method for optimizing those computationally demanding AI models that are currently intractable with classical computers. This could democratize AI development, allowing more researchers to tackle complex problems. We might see AI applications expand into new fields, like biology, medicine, and materials science. And the synergy between quantum hardware and software advancements could lead to unexpected innovations in various fields.
It's a vision of a future where quantum computing becomes an integral part of scientific discovery and technological innovation. And Schneepat concludes with a call for collaboration. emphasizing that realizing the full potential of QSGD requires expertise from multiple disciplines.
That's a crucial point. It's not just about building quantum computers. It's about developing the algorithms, the software, and the applications, and it requires collaboration between experts in quantum computing, machine learning, and various other fields.
So, a lot to be excited about, but also a lot of work ahead. Let's summarize the key takeaways from our deep dive into quantum-enhanced stochastic gradient descent, guided by Yurgo Schneppat's insights.
As Schneppat expertly lays out, QSGD offers a potentially revolutionary approach to optimizing machine learning models, promising significant speedups and efficiency, especially for those data-heavy and complex tasks. The idea of using quantum mechanics to compute gradients in parallel is truly groundbreaking.
But we also have to be realistic about the challenges. The development of robust and scalable quantum hardware is still ongoing, and integrating quantum and classical computing effectively requires significant effort.
Despite these hurdles, Schneppat's work highlights the transformative potential of QSGD across a wide range of fields, from deep learning and finance to material science and big data analytics. It offers new ways to solve complex problems, improve decision-making, and potentially democratize access to advanced AI development.
And looking ahead, as Schneppat envisions, we can expect continued advancements in quantum algorithms, hardware, and applications, leading to even more exciting innovations and a future where quantum computing plays a pivotal role in shaping our world.
It's a future where quantum-enhanced approaches like QSGD could redefine how we process information, make decisions, and push the boundaries of scientific discovery. Schneppat's essay is a compelling invitation to consider the vast possibilities that lie ahead.
A fascinating exploration indeed. And with that, we wrap up our deep dive into quantum-enhanced stochastic gradient descent. A big thank you to Yurgo Schneppat for providing such a thought-provoking analysis. Until next time, keep exploring the ever-evolving world of technology and innovation.
Keep those minds curious. There's a whole universe of possibilities out there.
Absolutely. See you next time on The Deep Dive.